So, hello everyone, I'm Eloi Moliner, and here I will talk about some alternative applications of diffusion models in the context of audio effects. So I will talk about audio effect estimation and automatic music mixing and see how you can use diffusion models for those. So, so about me, so I did my PhD at Aalto University. This is in Finland, although I'm not Finnish. But yeah, I worked on the audio signal processing team with Professor Vesa Välimäki, and the topic of my PhD was mostly focused on using generative models, more in particular diffusion models, for audio restoration. So I was going to talk about audio restoration, but I learned that there will be some nice talks about audio restoration, so I decided to talk about something else. Very recently, I did an internship at Sony AI in Tokyo, so I will talk about what I did there. And now I'm in reality labs research in the UK, doing something else. So in this talk, well, it's like a combination of two talks. I will talk first about using diffusion models for the estimation, for the blind estimation and removal of nonlinear audio effects. This is some work that I did with Michal Svento, who visited the lab last year, and we published these two papers in the Journal of the AES and DAFX. And the second part of the talk, I will talk about some more recent stuff that I did while being at Sony, of using diffusion models for automatic music mixing. So, okay, now was the first part. So here we're considering the task of estimating audio effects. So consider the case where you have pair data, you can see some observed wet signal, which can be, for example, some distorted guitar, and you also have access to the dry version of this, and you want to estimate the theta system, which is not known, or some kind of model of it. So this was quite popular during the last years, and I would say at this point it's a solved problem. So if you have pair data, it's quite easy, and it works very well to train a neural network to model this. You can be very accurate. But now I'm considering the case where we don't have pair data, but we only have access at different time to the observed wet signal. So this is a more realistic case, like for example, you listen to a record and you listen to a segment and there's some guitar or something and you want to recreate the effect. So you want to do it blindly only by having the wet signal, which is a much harder task because not having access to the source, it makes it highly ill-posed. So yeah, and the goal here is not only to estimate the nonlinear system, well, and the main motivation is to estimate the nonlinear system, but also we need to estimate the source signal. So there are some strong challenges here. First, as I mentioned, the problem is highly ill-posed, so there's an infinite solutions, infinite possible source signals, and infinite possible operators. Then even if this effect is known, it's generally not invertible, so you cannot really recover the dry signal having this one. Maybe because it would be like, for example, if you have clipping, it's not possible to retrieve the samples that are beyond the clipping threshold, for example, or maybe it could be something very, very hard. And yeah. Then, in order to solve this, we need some kind of prior about the source signal and about the system. And this will link about what Jean-Marie just thought about anterior aberration. We're using a very similar approach, if not the same approach for this. So here, how we focus on this problem, we first consider that okay, we don't have access to the original source signal given a sample, but we have unpaired data. So we have access to some samples from the source distribution, which are not the exact replicate of what you get. So yeah, we have the setup that we have a set of examples from the dry distribution, and then we may have only one example from the wet one, or we may have more than one, and that will, and yeah, so it will stabilize things if we have more than one sample. And then for the operator, we don't know that, but we can estimate it somehow. So we can use a model of that, which could be a neural network, or it could be something that if we have some information about what that is, we can design it. And the goal is to estimate these parameters that define this model. Now I can look about what other works have done to solve the problem, somehow correlated, not the same. So one is that this supervised parameter estimation. Here, what they did is that, okay, let's just train one neural network to estimate these parameters. So that's one neural network that the input will be the distorted signal, and that will spit out some parameters that will be part of this operator. And you can train that. Since this operator is differentiable, you can just compute the loss here after applying the parameters to the operator and backprop through the operator and to the neural network. So this is nice, but this requires that this system must be trained with a large data set of audio effects, and it requires that it generalizes to whatever we have at different time. So as I mentioned, we only consider that we have these two sets. We don't consider we have more information than that. So that is not the same task, because here you have to think beforehand how to train that model and make sure it generalizes. So it's a matter of building this huge data set with as many effects as you can and hope that it will generalize and interpolate. Then the other related approach is that instead of having a model that predicts the parameters, it's using a model that predicts some kind of representation of the effect. There's some very nice work about that. I will come to that later, in the second part of the talk. And then this operator model will be some kind of neural network conditioned on these embeddings. Yeah, this is nice, but it also has the same problem. In order to train this encoder, you need to train with a large data set of effects, and also you need to trust that this will generalize at some point. Another approach, which we will consider as a baseline, is this adversarial approach, which was proposed by some colleagues from Aalto. So here, what they propose is to optimize this neural network using adversarial training. So the idea is to optimize this parameter so that they minimize this distributional distance between the distribution of the wet sounds and this predicted distribution of wet sounds, which is the outputs of our model. And this distributional distance is parameterized with a discriminator. So if you're familiar with GAN, it's kind of the same thing. And this discriminator must be trained with this min-max objective, so that we iterate between iterations where we optimize this discriminator, so that it learns to differentiate what our model predicts and two examples, even if they are not paired. And then using the information from this discriminator to optimize the forward model. So yeah, they did a very nice work here. So by thinking about how you design this discriminator and the features that we do use, and so it's possible to optimize this being quite accurate. But then since it's based on adversarial training, our hypothesis is that this what we observed is that this would not be will get not very stable when the two pairs are not so balanced. So, for example, if y is much smaller than x, this training will be unbalanced, and the gradients of the discriminator will not be so useful. So we wanted to think about an alternative way to solve that problem. Yeah, and that's nice because it doesn't require of this generalization. So it only uses these two sets, and we can use this as a baseline to compare against. Then another approach that kind of motivates our strategy is to use this two-stage method. So you can first try to remove the effects with some other model for effect removal, and then using this pseudo reference you can do supervised learning. So this is kind of what we do, but that also relies on this effect removal model to generalize to unseen effects. So you also need to retrain that with a large data set. I wanted to avoid that. And another insight is that in order to remove well the effect, this model has to implicitly estimate the effect somehow. And also it may struggle with very ill-conditioned distortions, and this pseudo reference will be not so good, and that will also affect the optimization of this operator. So instead what we do is this unsupervised approach using diffusion, which relates very well to what Jean-Marie explained for the operation. So our idea is to first train one diffusion model, for example, with your guitar, with clean signals, and then use this diffusion model as a prior to jointly optimize the clean signal and also jointly optimize via expectation maximization this operator. So I can go very quickly through that. So this is just about explaining the terminology that we use for diffusion models. So we consider that this is consider one diffusion model that is trained from a Gaussian to the distribution, and this reverse process is parameterized with this score function. So what we have is one model that predicts the score function, this score model. And then at different time, when we do this posterior sampling, where we just replace this score with the score of the posterior. And as Jean-Marie explained before, this we can apply Bayes' rule, and this factorizes as using the prior score, which is what we estimated with the model, and also some likelihood score where we can use a model-based, sort of model-based approach for this. And for this likelihood score, we use this method proposed by Chang. When you just parameterize this likelihood with a cost function, and also this is a cost function between our measurements, the observed guitar signal, and what will be our reconstruction of the measurements given this x0 hat, which is the one-step denoised estimate at every step. And then we apply the forward model through that. And this gives us some gradient, and we can guide the process with this. But the challenge here is that we don't know this operator, so we need to optimize it at the same time. So if you're familiar with classifier guidance, it's kind of the same thing, but applied to inverse problems. Here I have some diagrams of how this is implemented in practice. So here I define this Z0. This represents here I'm talking about sets. So let's consider we have a set of wet signals, and this Z0 hat will be the corresponding set of paired clean versions of Y. And this is unknown, this is unobserved. So here's an example. Let's consider that Y is just some kind of very saturated waveform, and Z0 hat will be like in this case like a sinusoid. It's a very simplified case. Then I can define here some other sets of noise augmented versions of this Z0, which it just just applying noise to these underlying signals. And these are also unknown, but the ZT, the starting one, we can sample from this because it resembles Gaussian distribution. So then first we just train with diffusion model with another set X, set of clean signals. For example, you can just do some recordings with your guitar and train or fine-tune this diffusion model with that. That's what we do. This diffusion model it's a generative model that approximates this clean signal distribution, and we use it. So we use it as an approximator of this distribution somehow. And then we solve this problem using this expectation maximization, where we alternate with expectation steps and maximization steps. We initialize this process using sampling from Gaussian noise. In this case, since we have a set of signals, we need to sample noise for each of the signals of the set. And then we apply the expectation step, where we use this diffusion model. We use it to predict this posterior expectation. So this would be like one estimate of the clean signal given this noise, which if we have a model of the score, we can just apply this formula, we just go to this formula, and we can just get that with that. It's very simple. And that will be something that could more or less resemble the data distribution, but it's very smooth because this is like the mean of all training examples, and it will not be so good. And then once we have this estimate, even if it's not so good, we use that to optimize the operator through the maximization step, where we have this cost function between all the signals in the set. And then we iterate again. Well, we can update this latent variable using this ODE. So having our estimation of the posterior score, we can just apply one step. And then we iterate again, we do the exploitation step, and hopefully we'll get a bit better, and then we can optimize the operator with that. So yeah, so as Jean-Marie mentioned, we applied something very similar to this. Maybe there's some differences on the kind of laws that we use and how we initialize the process, the kind of models, and some other details, but it's kind of the same idea. We use that for iteration and input score estimation. Also, in some of my previous work in my PhD, we used that for music restoration. So we were able to blindly estimate some, for example, in the case of historical music, where we're missing some high frequencies and the data is has some resonances, and we are able to estimate some kind of linear version of these degradations. And at the same time be able to reconstruct the music. But in both cases we considered linear operators only. So it was kind of unexplored if we can make it a bit more complex and be able to estimate something that's more where we have less information, it's non-linear. So first of all, in order to explore this approach for non-linear operators, we studied the case of memoryless nonlinearities. And the idea was if we were able to estimate these memoryless nonlinearities in a blind way. With memoryless nonlinearities, I'm thinking about some distortions. For example, could be clipping. That's a more simple one, where the signal is just clipped or some threshold. This is a very simple one. You don't need a diffusion model to estimate that. You can just look at the histogram and see where it clips. But if this memoryless nonlinearity gets a little bit more complex, like for example, there it's not exactly clipped, but there's some soft smooth part here, so it's like soft clipping. It's hard to know that, or it could be something more interesting, like this kind of wavefolding where the waveform folds. So we're interested if we would be able to estimate that also, or something more, more weird like this one. And so our experimental setup is that we just train one diffusion model with clean guitar, and on the measurement set we only have 6 seconds. So in this case we wanted to make it challenging and have just very few data, and the task is to estimate the trace signal and the transfer function. So one thing that we had to think about is that, okay, which kind of memoryless nonlinear function operators can we use? We thought a bit about that. One simple thing to do is to use just a multilayer perceptron, just one neural network to optimize this. But then I thought that maybe it's a bit too much for what we need. And we looked at the literature, and there's this paper. They were estimating these memoryless nonlinearities, or in this case they had pair data, and they proposed this model which is just the sum of the 10H nonlinearities. So we tried that, and then since we noticed some limitations with these two, we also proposed this differentiable cubic Kelvin-Mulron spline, which was nice. I guess the idea behind that is that we can optimize the points of this spline parameterization, and because of this parameterization, because it's based on this cubic interpolation, it's smooth, and that was a nice property, because if this nonlinearity is not smooth, the non-smoothness will produce a lot of harmonics, and this lot of harmonics will complicate this blind optimization. But in this case, so it's smooth by design, and the idea is that this will be more stable. So we tried that for memoryless nonlinearities, and it worked very well in the end, so it was easier than we thought. Here we compared just using these different models, and you can see that we were able to estimate these transfer functions pretty well in some cases, especially using this CCR spline that we proposed, and also with the MLP. With the 10X model, since it's limited by design, it wasn't so accurate. So yeah, we tried different cases, like for example, hard clipping is the most simple one, soft clipping, but we also tried this wave folding. Quantization, where the signal is quantized, so if you look at the transfer function, it will be some kind of staircase. And yeah, we were able to estimate the quantization pretty good, and our estimate is because since so our hypothesis why this works so well is that since we trained this model with these clean versions of signals, and this model is so it's very sensible to how these waveforms look like. So, for example, if we train with some guitar signals which have more or less the same energy as the one that we expect, yeah, it would be easy to estimate this. Then one interesting case is this green line here in soft clipping. This looks like it's completely wrong, so polarity is opposite, but I want to argue that this is not wrong. The thing is that since it's blind estimation, what happened is that we estimated the dry signal with reverse polarity. Since we estimate with reverse polarity, that means that the system will also have reverse polarity. So yeah, we have to be careful with the loss function we use, I mean with the metrics that we use, because that will penalize a lot, but it's actually correct, or kind of correct, yeah. It doesn't happen so often because we initialized some of these operators so that the at initialization it was a Hellman identity. So it wouldn't always switch, but sometimes it will happen. Yeah. Then if you compare the performance using these different models, you can see that both MLP and CCR work pretty well, and the CCR worked a bit better, so the alternation would. So yeah, we didn't have any good baseline to compare this, which was not great, but then we compared, for example, on the clipping, which is a quite well-known task, at least for a speech. So what we wanted to see here is the clipped estimates are quite competitive with what we thought were state-of-the-art systems, or well, maybe not state-of-the-art at this point, but quite good speech restoration in the clipping systems. And if the clipping was good, that means that estimating well, it doesn't mean the same, but it would mean that estimating the operator will also be good. We have some baselines to compare against here. There's this DDD baseline. This would be a super biased approach. This is a bit cheating because it's trained only for clipping. So yeah, it's just one model that works one predictive model that works very well with clipping. So yeah, but we can see that with this STOI metric, which is pairwise, this one worked the best. But then we have some other baselines like this resemble model, which is based on some latent diffusion for speech enhancement, and this voice fixer, I think it's also latent diffusion, I'm not sure. But if we look at these metrics, using our approach both with MLP and CCR, it's a little bit better than these resemble and voice fixer methods. It's a bit better because this is about general speech enhancement, not just the clipping. But while our method also, for training, we don't have any assumptions for the clipping, it's just inference time conditioning. Then we also have NISCA, which is, I think it's a non-intrusive metric. Yeah, we can see that looking at the metrics, both for hard clipping and soft clipping, it's quite competitive with these models. Yeah. Then next we wanted to test if we can apply this for more complex nonlinear problems, or not just normalized nonlinearities. And for this we need a more expressive operator. So we can consider black box models. We consider this S4, which is a state space model, which was proposed for effect estimation using also pair data, and this worked very well, so we tried it here. Also, so this ungated convolutional networks, that it's also one of the most common methods for effect modeling. But then we thought that maybe this would be a bit hard to optimize blindly, and we also tried something a bit simpler, like this Wiener-Hammerstein model. It's simple, but it's also quite expressive. In this case, we used this Wiener-Hammerstein model is a combination of linear modules and nonlinear modules. So we have two linear time invariant models. This is just some filtering. We have some, it's STFT filtering, so we optimize the magnitudes of filtering the STFT, and we also optimize the phases. And then there's a static nonlinearity, which is parameterized with this splined model that I showed before. So, and then we compare against this adversarial method. Then the experimental setup, we try to be very close to what they did on this paper. So we use the same data, which is this IDMT SMT guitar dataset, which is just one single guitar. The dataset is quite small, so what we did is that we pre-trained this diffusion model with a larger, not so large, but a bit larger dataset, and we fine-tuned with that. And then we tested with 3 different distortion settings, which are the ones proposed in this paper, which have increasing severity. So there's clean distortion, light distortion, heavy distortion. And all signals are mono, sampled to 44.1 kilohertz. And we considered these unpaired datasets. So we have 16 minutes of dry. So we used these 16 minutes to fine-tune our model, and also to do this adversarial training. And for the wet one, we experiment with having different sizes of the wet set, so having 16 minutes also, so it's balanced with the dry, or trying to reduce that to 18 seconds. And we wanted to experiment on how the different approaches would work when we have different amount of wet data. Having less wet data would be more realistic, because in practice we will not have 16 minutes of measurements to do your same effect. Yeah. So here there's some results on, this is the light distortion setting. We have 3 different metrics. This is this AFX rep distance. This is a distance between one representation of the effects. And then we have 2 other, this is this MSS metric, which is, is these spectral distances. So it's basically computing some distance in the STFT at different resolutions. We have one on linear scale and one on log scale, which was interesting because it looks quite different. What we can see is that we have 16 minutes, both adversarial and diffusion approaches, they work quite well. I would say the adversarial approach worked a bit better. So the green one, this is the supervised case. This is the kind of the oracle scenario where we have paired data. In this case, it works very well usually because it's a very easy problem. And the blue one is the adversarial one, and the red one is with the diffusion model. And the different line patterns represent different operators that we use. So if we use this S4 black box model, the GCN one, or the Wiener-Hammerstein model. The Wiener-Hammerstein model didn't work with the adversarial one. It was not stable. But what you can see is that if you got 16 minutes, both work very well. But if you have less, this adversarial model just didn't work well because the data sets are unbalanced. While the diffusion model, the performance decreased a bit, but it remains quite stable. We can, in the clean distortion, I would say it's kind of the same thing. In the heavier distortion, this was interesting. The diffusion model did not work so well here, while the adversarial, it worked a bit better. Except if we look at the linear scale metric, in this case, the diffusion model worked better. I guess this depends on the loss function that we use for optimization. So I don't know if I have time to play some examples. Maybe at the end.
What is the x-axis in this?
This is the amount of data and the amount of wet data that we have for doing this optimization. So in the left, we have only 18 seconds of distorted guitar. In the right, we have 16 minutes. Yeah. So I will maybe play some examples later, but I don't want to spend time.
Just skip the presentation.
Well, I can play that now. So here I can play first the undistorted example. That will be the target distortion. So it's not so heavy, but it's a bit subtle, but with the diffusion model using the GCN 16 minutes we get this. And with 18 seconds we get this. if you try with the adversarial one, it doesn't work so well, I think. And with the Wiener-Hammerstein model, I think perceptually it was a bit better, I would say. Let's see how the example works. I'll play the target one again. Maybe I'll play another example which is more clear. Let's see. There's the lighter one. Yeah, that's the. Okay, that's the target distortion, and here what we get with the diffusion model, 16 minutes. And 8 seconds, no, 18 seconds. Now we can play with the adversarial, which doesn't. It's messed up. Well, that's adversarial with the 16 minutes. I think it works quite well. So yeah, it's a bit judged. Yeah, so it's a bit hard to judge by listening, but yeah, I guess you get the idea that it's not perfect, but it's kind of close. Yeah. All right. So okay. How can I? Well, I'll do that, I guess. Okay, so now I will go to the second part of the presentation, where it's about some recent work that I did while being at Sony this last summer. We wanted to use diffusion models for automatic music mixing. So the task of automatic music mixing is what I showed here. So we want to replicate the task of a production engineer somehow, where you get a set of tracks for each of the instruments. Automatically you want to estimate some way to balance the loudness of the tracks and how to equalize them all, or which effects to apply, so that the end result is it's a mix that will be something that a production engineer will do, more or less. And yeah, so this is what automatic music mixing is. We can look at what has done before on this area. So most of the methods that were proposed before this one were based on regression. People have thought about training these kind of models with different paradigms. So in this case, this F will be the model which input will be the dry tracks. You can try to predict directly the mix. And then just have one black box in a network where the input will be the sources and predict directly the mix. Or another idea is to use this parameter prediction. So the model will just predict some parameters of some audio effects, and then you just have the ground truth parameters and you just regress to that. Or alternatively, you can do the same parameter prediction but have a differentiable pipeline. And since it's differentiable, you can compute the mix in the audio waveform and have the loss in the waveform domain, and that turned out to be a bit better. But my point is that this mixing is it's a highly subjective task. So there's no single good solution. So every mixing engineer will do whatever he thinks is good. So that means that there will be multiple, what I will say, valid mixes or plausible mixes with some input tracks. And this is driven by some artistic choices, or whatever these engineers would think. So yeah, it's not a one-to-one mapping. And our models based on regression just try to search this one-to-one mapping. These regression approaches will kind of predict this kind of average of the training data, because if you do regression, you do regression towards the mean, or it depends on the kind of loss function that we use, but some kind of average of what has been in training. But this average would not be a plausible example. Then there was an alternative paradigm which was quite popular in the last years, this mixing of style transfer, which I guess it made a bit more sense. So in this case, they have a reference mix, and the idea is just not to do blind automatic mixing, but to mix like this reference one. So yeah, this is very nice, but I would say it's a different task. So in this case, you need to first find the suitable mix and then do this mixing style transfer, but it's not completely automatic mixing. Yeah, so instead, what we wanted to do here is try to do this probabilistic or generative approach, where just have one model that is able to model the distribution of all possible mixes seen in the training data. Yeah, that's how we formulate the problem. So we have a set of dry tracks and a set of wet tracks, and there's these unknown effects that we would apply for each of these tracks. And the idea is that adding this set of effects, which is unknown, will produce a mixture, and this will be something plausible or not, depending on the data. So what we want here is to estimate this probability distribution of the wet tracks given the dry tracks. So yeah, we want to estimate this P of y given x. Our assumption is, well, first of all, we assume that these effects are time invariant. So, for example, you just apply the same equalization for the whole track, which I guess is quite realistic in some cases. So it doesn't count for cases where some engineer will change some parameters during time varying. In this case, it's not time varying. But yeah, we have this data-driven assumption that we have access to a data set of these professionally mixed wet tracks. In this case, we had a pretty large data set. And then we have a smaller data set of paired dry and wet tracks. And okay, so we want to estimate this probability distribution. So one thing that we could be tempted to do is just to train one end-to-end generative model to do that. Like, for example, we can do flow matching or something like this, but I would say that having this end-to-end generative model in the ambient space would be all the way from a spectral line suboptimal, because mixing decisions are quite, it would be totally entangled with the content, and that's not what we want. So having a system like that, it will just do hallucinations, it will change something about the music content, and we don't want, and we only want to change the effect part of this. So what we propose is this method, which is called Megami. I was told Megami means goddess in Japanese. So yeah, it stands for multi-track embedding generative automixing. And so as far as we know, this is the first time that someone proposes a purely generative approach for automatic mixing. And what we did here is a factorized design that we did this generative model only on some latent space which is injective only on the effect information. And this separates, so it separates the mixing decisions from the musical content. So yeah, and then we have a second stage where we do this decoding, which I will go through that later. So at the core of this system, there's this multi-track effects embedding generator. So this is just a conditional diffusion model, or more like a latent diffusion model. What we do is that we generate sets of effects embeddings, one for each track. So it's one conditional model that is conditional on some representations of the dry tracks, and it spits out one embedding which contains information of the effects for each of the tracks. So what are these embeddings about? This is the same idea as I introduced in the start of the talk. So this is some representations that are trained via contrastive learning or some other strategies. Basically, what we use is based on contrastive learning. So they train to disentangle, to only capture effect information. We use these effects encoder ++, which was proposed quite recently from some colleagues at Sony. The idea is that we just take the ground truth wet tracks. We can just apply this encoder, and we will get the ground truth embeddings. This is what we use for training this diffusion model. And In addition to that, which is a 2048 dimensional embedding, we found that it's pretty good, but it's not so sensible to some aspects which were quite important for our application. So it was not so sensible to the dynamics of the effects. So, for example, it didn't have much information of the loudness. So we also included this log RMS information, so it has some information about the level of the signals. And just because why not, we added some other features like crest factor, dynamic spread, and so on. So this is what this embedding contains. Then this is conditioned on some representations on the content of the dry tracks. In order to make things easier and not just input the whole dry track there, we introduced just clap. The idea is that our idea is that this model will be conditioned on some information on the semantics of each track, and then it will produce these effects for each of the track types. And this is nice because in this case we don't need to label the data. So we don't need to first think if these tracks are drums or bass or something else. You can just clap and just rely on the information that clap can extract. So it's quite flexible. So the number of tracks that we can use, I think we trained with up to 14, but if we wanted, we could be even more. And it could be any kind of instrument. So this was the content encoder, and then we used this. So we trained this latent diffusion model on this embedding space. We use this EDM formulation, but we could use something else that flow matching, but it was more or less the same. And at different time, we do this probability flow ODE. So we first sample from Gaussian noise at each of the tracks, each of the embeddings, and then we just generate the embeddings. One detail is that in this case we're working on sets of tracks, so the number of tracks that we can see is not fixed, so we can run inference with only 3 tracks or up to 14. But since the architecture is it's a transformer, it's permutation equivariant, we can do that. So it's just about how to design the architecture. You can see a variable number of tracks. So that's how we designed the architecture. So it's permutation equivariant. There's some tricks. You can read the paper if you're interested. We did cross attention with these content representations. So one important detail is that by default, training this model, as we see it here, we need pairs of wet tracks and dry tracks. The problem is that there's not that much available. Yes, there's not that much data which is available with pairs of dry tracks and wet tracks. It's very hard to obtain. But instead, there's a bit more data available. Well, at least internally, we had a very good data set which contained wet multi-track data. For example, you can look at some data sets used for source separation, and this is the kind of data that you will see that. So the idea is that maybe if we can find some kind of trick to train the generator only having wet multi-tracks, so not having the X one. And there was some work proposed by some colleagues at Sony before doing this kind of effect normalization. So we were looking into that, and what we proposed is this domain adaptation strategy. The idea is to do some domain adaptation on the clap representation space so that we can extract the clap embedding from the wet track, and that would be equivalent to extracting the clap embedding from the dry track. So we proposed this domain adapter called T, which is very simple. It's just one very small MLP operating in the clap representation space. And the task of this adapter is to remove the effects in the clap space. It's just one regression model, so it's trained with an L2 loss. It's very simple. You get the clap embeddings from the dry track, the clap embeddings from the wet track, and just want the two of them to match. And the thing is that we found that this was not enough, and in order to make sure that the two distributions were the same, we just added noise to the added embeddings. So we added noise to the embeddings, and that spreads out the distribution. And after adding noise, the two distributions are kind of similar, and that's what I showed in this equation. So here I show the probability distribution of the adapted club embeddings, and this from the dry club embeddings. Here this is a Gaussian kernel, so it's just convolving this distribution with a Gaussian kernel. After doing that, the idea is that the two of them would look the same. And we found that just training a model like this kind of did, and that was enough for our purposes. There's some limitations though, so adding noise here, it will maybe mask some information on the club space, some details, but hopefully not too much. Then the last part, so we have this model that generates embeddings, but we need to decode this embedding somehow. We use what would be like one, so this effect processor, you can think about an effect decoder. So it's just one model that we can input the dry track and also the embedding, and it will spit out the wet version of the track with this with information and the effects from this embedding. So here we just use a predictive model based on just one black box model. Use this model based on temporal convolutional neural networks, which was shown that it was working well for effects before. Conditioned on these feature modulations. This was trained with these multi-scale spectral laws, also with this deep feature laws, so we want to make sure that the effects encoded representation at the output is consistent with what is in the embedding. And then what questions you can ask, so we have been talking about generative models. Why is this not generative? Why is this just predictive? So our assumption here is that all variability in the mixing is just comes from the embedding. So and the idea is that all variability that we're interested on is encoded here in Z. So what we assume is the condition on Z, this mapping should be deterministic. In practice, it may not always be, but there's the assumption that we have. And it's also good that it's deterministic, so that this way we prevent this model from introducing some hallucinations that is not wanted. And that's also nice because it's very general. We can train one single model that could apply for any kind of track. We also condition it on the lab embedding because it works a bit better, but it's not that important. And then we can just apply these for as many tracks as we have. Here, there's a summary of the. So in the end, the way that we estimate this probability distribution that we first introduced is summarized with that. So this part is our diffusion model. Then we marginalize over Z, and then we have the second part, which is the second part effect processor. So it's deterministic that this is why this is a delta distribution, and it's independent for its track, so this is why these are multiplied. This is just how we ended up doing that. Then we run some objective evaluation, but it's a bit tricky to evaluate these things because it's the first time that we have thought about it from a generative perspective. So for evaluating that, we have to take into account that we want to match the distribution of mixes and not really some pairwise similarity, because that will be so good. What we did is that we have a benchmark with 59 songs, seconds of 11.9 seconds, just because we have to choose something. 10 segments for each song. We had the stereo tracks, some of the 44.1 kilohertz. As the metric, we have this KAD metric, which is based on maximum mean discrepancy within the distributions. Compared to, maybe you're familiar with FAD, which is kind of similar, but FAD it's not so. I mean, if your sample size is not so large, it's quite unbiased. But KAD, on the other hand, it's a little bit better. That's why we use that. So what we did is that we started some embeddings using different kind of representations from the mixes, and we just compute this maximum mean discrepancy between the distributions of embeddings. So we have some baselines here that we compared against. Also using these different data sets, so we train with some internal data sets. Have one smaller version. In the smaller version, we have pair data, and then in the large version, we only have wet data. So something interesting here is that, I mean, with our approach called Megami, we are better than these previous baselines, at least these metrics, basically because the approach is generative, not like the other ones. Then if we compare the results when using the large data set and the smaller one with pair data, we get some improvement with the performance, with all the metrics, which was good, which meant that having more data, even if we have to use this domain adaptation, it was helpful. Then we also tried training with a public data set. It was kind of working, but not as well. So so it's good when you have a lot of data to train on. But since there's not that much publicly available data, the performance is a bit reduced. But it still kind of worked better than these baselines, at least in this evaluation. Then we ran some subjective evaluation, since, this is a very subjective task, so having objective metrics, it's not so reliable. So what we did is just to ask people what they think that sounded better, or at least to rate the different mixes in terms of production value. That's also very subjective, so it depends a lot on who you ask, but at least we try to do that. So we ran this kind of test, we have these different mixes and people were able to rate them. These are some results that we obtained, which were, what we found is that our approach, the Megami one, when trained with the large data set, on average the scores were quite similar to the human mix. So people liked it as much as the human mix on average, but the results depends a lot on the example, because of the natural fit. Maybe we are lucky and we sample with this diffusion model and we get a mix that people will like, with something that maybe it's plausible according to what is trained, but maybe they just don't like it. So the results were a bit surprising. This baseline FX normal to mix didn't work as well as we expected. At least people didn't like it in some cases, like in the country example or the jazz one. This other baseline, the equal loudness, which was supposed to be a low anchor, just about mixing all the tracks with equal loudness. It's supposed to be very bad, but in some cases, like the disco one, it just worked. So that was a bit surprising. And then you have this other baseline, this end-to-end flow. Here we try to train one end-to-end model. Instead of doing this factorized approach, we train one model based on flow matching between the two distributions and see how it went. And it kind of worked, but it was introducing some hallucinations, and there were some artifacts that people noticed. All right, so how many time do you have left now? Okay, so I will play some sound examples. Yeah.
For Britpop, this means that British producers mix his songs really bad.
This mix, people didn't like it. I guess it was not a good one. It's one from this MedleyDB database. I don't know. I guess it was not a good mix. Okay, so here there's some examples. Okay, I can play the rock one. So here there's maybe I can play the Britpop first, since we were talking about that. That's what the human did, at least on MediDB. Okay, and that's what Megami does. Here is this baseline, the FX normal to mix. That's a predictive model. And that's with this end-to-end model. Here, so maybe it's not so easy when you listen in this environment, but if you listen in an isolated place with headphones, you can notice some artifacts, some very little artifacts, and that's also with the equal loudness case. so balanced. I can play also the disco one where the equal loudness turned out to be good. First I can play the human one. And that's the equal loudness one. And that's with our method. So one interesting thing is that since this is a generative model, you can sample multiple times and you can get different kind of mixes every time. Hopefully these mixes would be good or well, they will be more or less good depending on how lucky you are, but yeah, you can get an idea of what was in the data by sampling different times. Yeah, I can play one example. For example, yeah, let's play the disco one since I play one example. Maybe there's some differences, like the panning. Maybe in some examples you could pan the guitar to the left, to the right, or you will add more reverb or something like this, and yeah, this will reflect here. Maybe there's time to play another example. Which one? The rock, maybe. I will play first the human one. With the Megami. And I can play some more examples here.
In the mixing engineering world, like we say that the mixing starts with a recording, and I wonder, yeah, like if I give my shitty recordings to this thing, will it still do? Because there will be some sort of distribution shift. I wonder if you have considered this in the data pipeline, if you have some corruption augmentations to yeah, because I guess you are working with professionally graded recordings.
Right, yeah. For this, what you will need to look at is, so ideally, if you extract these clap embeddings from these recordings, yeah, there would be a distribution achieved, but maybe with this adapter, this will go out, with the noise will go out. The thing is that maybe the processor that will, I mean, it will not work as well if what is seen as a dry track is not as the, yeah, what is retrained. So I think
I guess this could be easily reproduced in an augmentation pipeline.
Yeah. So I think I did that a bit. I don't know if the end version of the model had that feature, But yeah, it's just about applying some augmentations to the inputs and make the model robust to that. So basically, it will change the effect style, being independent on how bad your recording is. Yeah.
Yes, one last question. Like, I didn't get it completely. How do you get the content invariance in the effects embedding? Like, you said you use only the wet or the professional, like the mixed. But I guess for this contrastive learning paradigm, you need some positive and negatives. I guess you need the same mixes applied to the same content. Different mixes applied to the same content, so that you can have the positive pairs that they have to have different content, no?
Yeah.
Otherwise, so I guess you do random mixes or for the.
You mean for this domain adaptation?
No, for the content invariant, the embedding effects embedding.
Content variant effects.
Like you have these
okay.
effects embedding that
yeah,
remove the content.
I did not do that.
So I guess you need the same effect applied over different contents.
Yeah.
And for this you don't have. You need to create these. No.
I did not train that model. It was from previous work, so I'm not the expert on this. But yeah, I think what they did is that they get positive pairs of different contents and just maybe a contrastive learning so they match.
For this, they apply different effect strips.
Yeah.
To the same content.
Yeah. So they have.
This randomly is created.
Yeah. So they have a large pipeline of audio effects, and they just made this model.
Randomly create.
Yeah.
Effect parameters and.
So a quick question related to the standard deviation of your outputs, right? Like it's nice and stochastic, and you get like some distribution that like an end user would choose from, and etc. Actually, funny enough, like one of the outputs was really sounding like the equal loudness mix at some point. I mean, like the standard deviation is still pretty high.
Yeah.
And I was just wondering, like, have you considered typically using a clap embedding or like a textual description of the mix, like a text conditioning for the final mix? Like you said, like you want something more bright, you want something with more like drums and all this sort of stuff. So you don't have like to improve that granularity directly like in the cell, like in the tracks, but let like this guide, let this conditioning guide your diffusion models.
So it would be possible to that. I mean, I didn't do that because there was no time. It wasn't out of scope. But yeah, it would be possible to condition this model either at the training time or different time. So you can apply some guidance, for example, some text conditioning or something. Yeah, it could be done. And I guess it would be a way to make this more usable and controllable, I would say.
Okay, one more question, and then we have the coffee break.
So it sounds like the equal distribution is equal loudness is kind of reasonable, right? In most cases, or
well,
yes.
If you ask an engineer, he will not agree.
We can hear it. But like, are there like general trends? What should be the balance between different instruments? So, for example, like what's the typical predicted loudness for voice or for drums? Is there some sort of pattern there? What's the kind of desired?
I guess there is, but I'm not the expert here.
I think for dance and pop music there is for sure.
This is where it enters the fact that you have a nice recording, no? That you, loudness normalization, you're not bringing up a lot of garbage noise because you record it with not enough dynamic range or whatever. If you have properly recorded data, this loudness baseline, I guess it's already pretty good, no? And if I use my recordings, no?
Yeah, but I'm asking, is there like a typical weighting between different instruments that's characteristic of good mixing?
So something that has been done before this AI mixing thing, before using networks, people propose some rule-based systems. So yes, and this is defined some rules based on some feature extracted from the inputs, and based on these rules, they just did this mixing without needing data.
Yeah.
So I guess this is super related to it, But out in practice, so not the one who works on doing these mixes. I just work on this data-driven project, so I don't know what real engineers would like or not. Yeah.
So it would be interesting to see that, like, a kind of a distribution. What's the weighting, typical weighting, or something? I don't know if there is.
It would be interesting to study that. Yeah.
Oh, thank you, Eloi.